All right, let's dive right in. Today we're looking at an injury that's surprisingly common, but also incredibly tricky to get right. A break at the very base of the jawbone. We're going to unpack some fascinating research that introduces a whole new way to fix these tough fractures. So, to kick things off, let me ask you this. What do you think is the single most common and at the same time one of the most complex fractures you can get in your jaw? It's an injury that, if it isn't treated just right, can seriously mess with your daily life.
And there's our answer. The mandibular condyle base fracture. This is the spot, right here, where your jaw hinges to your skull. When this piece of bone snaps, it can throw your whole bite out of whack, make chewing a nightmare, and even affect the symmetry of your face. It's a big deal.
Here's how we're going to break it down. First, we'll look at why this spot is the jaw's weak link. Then we'll get into the tricky anatomy that makes it so hard to fix. We'll explore the wild history of trying to put it back together before we get to the really cool part, an elegant new design and the incredible results it delivers. So let's start with the scale of the problem. Just how common is this injury? To understand why it's such a weak link, we got to look at the numbers. Check this out. These condylar fractures can make up almost 40% of all jaw fractures. That is a huge slice of the pie. It means this specific spot is a fundamental weak point in our facial skeleton. It's just prone to breaking. And for someone going through this, it's just completely disruptive. This quote from a real patient case says it all. Your bite is off. Your front teeth don't even touch anymore. Think about that. It impacts everything. How you eat, how you talk, everything.
Okay, so why is this so notoriously hard to fix? Well, a huge piece of the puzzle is that not all of our jawbones are built the same, which, as you can imagine, makes treatment a real challenge.
It turns out our jawbones basically come in two main flavors. You've got the tall, slender type, and you've got the short, squat type. Each one presents its own problems for a surgeon trying to attach a metal plate. It immediately tells you that a one-size-fits-all approach is just not going to cut it. And if that wasn't complicated enough, for years, the very system surgeons used to classify these fractures were just wrong. The official guidelines didn't actually match how the bone breaks in real life. This meant really severe fractures were getting misdiagnosed as simpler ones, leading surgeons down the wrong path from the very beginning.
So you've got this mix of tricky anatomy and flawed diagnostic tools. And what you get is a perfect storm. It led surgeons into this totally chaotic world of treatment options, all trying to achieve one thing: stability.
Get this. To fix this one type of fracture, surgeons had to pick from over 51 different kinds of plates. Can you imagine? It's like trying to build a Swiss watch with a giant, messy toolbox full of random parts you've never seen before. Just chaos. Now this is where it gets really wild. Researchers decided to test all these plates against each other, and the results were shocking. The most stable option was over 15 times more rigid than the least stable one. That's not a small difference. It's like giving a surgeon the choice between a steel I-beam and a wet noodle to hold a patient's jaw together. So when you're faced with a situation this messy, you realize you can't just pick a better part from the pile. You have to go back to the drawing board. You have to engineer a whole new solution from the ground up, based on science. And the first big aha moment was a total game changer. It came from research that identified what's called the ideal lines of osteosynthesis. It's a fancy term, but the idea is simple. It's about finding the bone's natural stress lines, the pathways where it's strongest, and realizing that that's where you need to put your support. So they basically mapped out the bone's structural blueprint. There are two lines everyone knew about: a thick edge that handles compression and a thin edge that handles tension. But the real breakthrough is embracing a third, often ignored line, a natural reinforcement that runs diagonally down the bone. This gave them a perfect third axis of stability to work with. And you can literally see the idea evolving here. We went from surgeons trying to juggle two separate plates to some early attempts at a single plate, all the way to the final product, the triaxial plate, or 3AXP. It's the culmination of all that research, integrating those three ideal lines into one single, elegant piece of engineering. So here it is, the 3-axis plate. Those three arms are designed to line up perfectly with the bone's strongest pathways. It's held in place with 11 different screws designed for different bone thicknesses. But what's really brilliant is the principle of load sharing.
The plate doesn't just shield the bone, it works with the bone, sharing the forces of chewing. This actually encourages the bone to heal stronger and more naturally.
And the proof is right here in these virtual stress tests. With the old plates, you can see all the stress, the red areas, dangerously concentrating right around the screw holes. That's where they fail. But look at the 3-axis plate. The stress is channeled away from the holes and onto the solid metal arms. It's just a smarter, stronger design. Okay, so the engineering is impressive. The theory is sound, but how does this actually play out in a real person with a real injury? Well, let's look at a pretty incredible recovery story. So the research followed a 42-year-old basketball player. He has his surgery, the next day he goes home, and just 8 days after leaving the hospital, he's back to his professional activities. 8 days. 5 weeks later, full recovery, perfect bite. That's unbelievably fast. And here, right here, is probably the most powerful result for the patient. Because that new plate was so incredibly stable, his jaw was wired shut for 0 days. None. Anyone who has ever had their jaw wired shut, or even just imagined it, knows what a huge leap forward this is for comfort, for nutrition, and for your sanity. And this isn't just about feeling better. The numbers back it up. Before the surgery, on a scale of jaw dysfunction, he was at a 3, which is significant impairment. After he recovered, he was at a 0, a perfect score. His jaw function was completely restored. Now let's zoom out and look at the big picture. When you compare open surgery, like with the 3AXP, to the older, non-surgical approach, the difference is night and day. Nearly 3/4 of surgery patients have no complaints later on, but look at the long-term joint problems. A staggering 62% of non-surgical patients develop them. And the reason is simple. Open surgery allows for what's called anatomic reduction. It means putting the bone back together exactly how it was meant to be. And this brings us to a really powerful final thought. When you have a technology that can perfectly restore anatomy, prevent decades of future pain, and get someone back to their life in a matter of days, it really changes the conversation. It makes you ask, is avoiding that treatment really a choice? Or is it a compromise on a patient's entire future? It's an incredible example of how brilliant engineering can completely change what's possible in medicine.